Okay. Yeah. So okay. So we were studying this potential chapter, right? So that is the second chapter after this Coulomb's law and electric fields. So we will do some of these problems through which we will clear some of our doubts. Okay. So so let's first do this problem. So here, so there is a non-conducting rod of a given length and uniform linear charge lambda. Assume that the electric potential is defined to be V is equal to 0 at infinity. What is the V at point P at a distance d at 8 centimeter? So like here. So what is the potential here? Okay. So the first one is really easy one. So what we do is, so assume that this is our this rod, okay, non-conducting rod, and assume that there is this this element, okay, which we are calling as our dq. So for this dq, at this p point there will be dv potential which will be generated, right? And so how do we write this? We just write 1 by 4 pi epsilon 0 and dq by r, where this r is given by this Pythagoras theorem, x square plus d square and square root. Okay, this is x d and this is r, which is the square root of x square plus d square. Now to get the net potential of this whole rod, which goes from minus L to plus L, what I have done here is I have integrated over this small dv. So when I do that, what I get is we just integrate here minus L to L. I just plug in everything. I just plug dv here. Okay, and you see that this integrand, this is an even function. So when there is this even function, what you can always do is you can just take 0 to L limit. Okay, someone else is joining probably. Yeah, let me add. Yeah, it's Ansh. Okay, yeah. So yeah, Ansh, we are starting. Okay, so I think you have already seen this one. Yeah, so let's just do this. Okay, so you know how to integrate this thing, right? So this is just a logarithm of x plus d x square plus d square. You just plug in those values and you get what is the potential at this point, right? What is the potential at this point? And so, and there is the second problem which is also related, which also talks about a rod, okay, which has some charge. So this has some plus lambda charge density, as this has minus lambda charge density. So, and they are asking to calculate the potential at this point P. Okay, so we will do this thing similarly. We will assume that there is a dq charge. Okay. Now here the dq is actually x dependent, because you see on the right hand side, on the left hand side we have some positive charge, and on the left hand side we have some negative charge. So for the dq, we can write this thing as some lambda, which is a function of x, or you can just directly write lambda times this sine. Okay, so for that sine of x, and we gave it a minus sign. So sine x function is what? Sine x function is just tells you the sign of the given variable. So that is just 1 for positive values and minus 1 for positive values. Okay, so for minus x, what we have is we have some positive charge, so we have just plug minus lambda sine x here. So that takes care of that linear charge density. Now we don't need to do this integration. So I will show you this trick that if you just look at this integrand, right? This integrand is right now an odd function. So when there is odd function in between a symmetric limit, that always is 0, right? So we are doing this without any steps. You can directly say that okay, the potential for this kind of configuration is 0. Okay, so let's move on to the next one. So if you at any point if you have any problem, so just ask me, okay, and yeah, just unmute your mic and ask me. Okay, so the next one. So this figure shows a thin rod with a uniform charge density of 2 microcoulomb per meter. Evaluate the electric potential at point P if D is equal to capital D is equal to L by 4. Okay, assume that the potential is 0 at infinity. So we will here also do in the same way, but here the limits will be slightly different. So like here, so let's say this is our rod, right? So the whole thing is our rod, and here also I have chosen this dq element, which is given by lambda times dx. Okay, And so this thing is same like the last one, but here because this rod is now starting from some D and it is going up to L, so we will have to plug those appropriate values, and we are measuring our potential at this P point. Okay, so yeah, so this is our X, this is our X, and this is our D, and this is our R, which is given by x square plus d square square root. So you see, you can just directly integrate this out, right? So when you integrate this and you plug in the values, you get something, right? You just apply standard formulas of your calculus, and you just apply this limits, and you get this result. Okay. Okay, so let's move on to the next one. So this is a okay, what is this problem? 3 thin plastic rods form quarter circles with a common center of curvature at the origin. So they are all concentric, all these circles are concentric, and they are considering only quarter of the circle. Okay, so this is just 1/4 of the circle, and the charge distribution on all of these plastic rods are given. So the Q1 is some number 30 nanocoulomb, Q2 is 3 times Q1, and Q3 is minus 8 times Q1. So you see, the easiest thing about working with potentials are you can just add them up. You don't have to think about what are the directions, because these are just scalars. So what you have is for this circular for this circle, what you have is you just have a potential 1/4 pi epsilon 0 times total charge on the arc divided by the radius. Okay, so what I have done here is I have just plugged in Q1, Q2, Q3 with their appropriate radiuses. Okay, and when you sum it up, then this gives you the net potential at this concentric point. Okay, so this is very easy. So just remember this kind of thing, that for any arc, if you measure the potential, so if the arc has total net charge Q, then the potential at this point is nothing but this 1/4 pi epsilon 0 Q by R. Okay, so let's move on to the next one. So again, another rod problem. So there is a thin plastic rod of length 12 centimeter and uniform positive charge Q is equal to 56 femtocoulomb lying on x axis. Okay, with V is equal to 0 at infinity, find the electric potential at point P1 on the axis at distance d is equal to 2.5 centimeter. Okay, yeah, so right, so okay, so they are asking to calculate for these 2 points, one is here and the other one is here. Okay, so yeah, so let's see how to do this. So here also what we will assume is that there is this small element. Yeah, so this is our dq. So dq is given by lambda times dx, and the distance when you are measuring from this P1, the distance is just this this x, right? Now, but for the x, what we will have to do is we will have to, if you are sitting here at P1 point, then you will have to substitute these proper limits. So because you see we are going from, so the rod is going from some d to d plus l, right? When you are measuring from, this is your origin. So what I have done here is just I have plugged in lambda dx by x, and this is just a simple integration that gives you just the log, and you put the proper limits and you get something like this. Okay. So similarly you can calculate for this P2 like I have shown you in the last two examples. So you calculate the proper distance r from here, and you integrate from this point to this point, and you plug in the values. Okay, you try to do that. Okay, yeah, okay, yeah. Okay, so let's talk about this one. So yeah, this is a funny looking problem. So what we have here is a smiley kind of configuration, right? So there is a arc sitting here, there is a dipole sitting here, and there is a whole circle sitting here, and they are asking to calculate the potential at this point, right, at the nose of this smiley. So how do we do this? We calculate the potentials for each element, and we consider the superposition principle, and we just add all of these potentials up, right? So okay, so let's say for first of all the dipole. Okay, so the dipole, right? So this dipole. So for the dipole, what we have here is we have p cos theta by 4 pi epsilon 0 r square. So this is what you have for a dipole. So they have already given the value of p, I guess. Yeah, so they have already given the value of p, right? And the theta, if you are talking about this theta, you will see that this theta is actually 0 degree. I mean, if you measure, so okay, so let me just talk about this angle once. So when you're talking about this cos theta, this theta is actually this angle, right? Yeah, this angle is cos theta, right? Yeah, I think, yeah, this is right. No, okay, not this one. I think, yeah, this one. This is the cos theta. This is the cos theta that they talk about. Okay. Now, when you are measuring anything at here, exactly at this perpendicular point, then this theta becomes 0, right? And this cos theta becomes 1. So you can just throw this cos theta away for this configuration. And for the arc, so as I mentioned before, for the arc, this is very simple. This is just the total net charge on the arc divided by the radius of curvature. Okay. And for circle also, this is again similar, but the charge will be different, right? So let me denote q1 here and q2 here. Okay. So you have these three components. Okay, not components, these three potentials for each of these three elements, right? So what you do is to get the potential here at this point, at the nose of this smiley, you just add all of these three, right? I think that is clear. Okay, so there is also this other problem. Okay, let's see what they are talking about. So what is the net electric potential at the origin due to the circular arc of charge q1 and the two particles of charge q2 and q3? Okay, so how do you do this? So first of all, they are asking to measure the potential here, right? So you see, you already know how to calculate the potential for this circular arc. You also know how to calculate the potential due to each of these charges, right? So for this angle, for this q2 charge, there is a slight angle. So you will calculate what is the distance from this point, and you will just plug that in, right? And you will sum it all up. Okay. So you can do this part. This is a simpler one. Yeah. So these potential problems are very simple, not that much tough. So let's go to this is a similar kind of expression. But the little twist is that on this rod, the charge is not distributed uniformly. So the charge goes like linearly. Okay. So that means that as we go along, so the charge actually increases on this side, and here the charge is very small. But as you go on this right edge, this charge becomes times C times L. Okay, and here the charge is 0. Okay, so for this, how you do this? So the recipe is exactly same. You will again consider a dq element. For the dq element, you will consider what is the potential, and you will just integrate over the whole limit. So here so they are also asking to calculate for these 2 points, I think. Yeah. So yeah, for p1 this is straightforward. Again, you will have to do the same kind of calculation, but you will have to plug in this lambda which is now c times x. And you do this integration and you obtain the result. Yeah, as simple as that. Okay, yeah. So yeah, this kind of problem, I have a lot to talk about. This kind of problem where some electric potential is given and you are asked to calculate an electric field. Okay, so these are very easy problems, but yeah, let's see how to do these things. Okay, I think you probably don't know this kind of notation. So this is called grad. Okay, so this is called a grad. So this is a mathematical operator. Okay, so this grad operator operates on scalar quantities, scalar functions. I mean, that doesn't have any directions or something like that. Okay, and that gives you a vector. Okay, and how to operate this on any scalar? So like if you have a function that is a function of, let's say, variable x, y and z, then what you have to do is you have to take the partial derivatives. Okay, so partial derivative means on the first one you have to just consider x as your variable and you consider y and z as constants. You will not take any derivative of them. So the first one you will have to take a derivative with respect to x, the second one you will have to take derivative with respect to y, The third one, you will have to take a derivative with respect to z, and with all of these things you just add a proper I, j or k, meaning which direction you are taking the derivative, you just multiply with that unit vector I, j or k. Okay. So like for this example, so this simple example, we have only two components, we have only this v is a function of two variables x and y. So when this is a function of x and y, so we don't need to consider these three terms, so we can only get away with considering only two terms. Okay. So because this is a function of x and y, the first term we will do is derivative with respect to x, and remember there was this minus here before, right? So you take a derivative with respect to x, you just multiply unit vector I hat, and you take a derivative with respect to y, and you just multiply with a j hat. Okay, and you just take the derivatives, partial derivatives. So partial derivatives del x, this means that we will only differentiate on this x. Okay, we will just differentiate take a derivative of this x. So what does this gives us? This gives us 2x times some constant number, which was 2 here. And for the second part, what we will get is we have this 3, which is a constant number, and the y square, which gives us 2y. Okay, and at the end of the day, you just plug in the values that they have asked to put you in. So you just plug in that value and you obtain what is the electric field. Okay. So basically, yeah. So just remember that the fact that you can to calculate the electric field from the potential, you will have to take a grad of the potential, a gradient. So you can look it up. You can search gradient. A gradient of a let's say scalar. So yeah, this is the proper way to calculate the electric field. Okay. So this kind of notations are these kind of notations appear in some higher studies of this vector algebra. So this is called vector calculus. You see, we have some vectors and we are also doing the calculus. So this is called vector calculus. Yeah, but you don't need to know much about this right now. So there are some other more kind of variations of this operator, but yeah, this will work for now. So you just remember this is a grad. Okay. So similarly, so we have done in Cartesian coordinates, right, where we have some x, y, right, and we know that there is a this rectilinear coordinate system which we call our Cartesian coordinates. So for Cartesian coordinates this works. Okay, but let's say you are given a potential which is in plane polar coordinate. So let's say you are given a potential which is in a function of r and theta. So how you would do this? So to do this, just pay a little attention here. So the first component will be, we will have to take a derivative on this r, so del r, and the direction will be given in this direction, right? So we will have to plug in an r hat. So similarly, we will also have to take a derivative with respect to theta. So we will take a derivative theta, and there is this theta hat, but so due to there is some scaling reasons, there is 1 by r, which I don't want to get into right now. So just remember that whenever there is this del theta, you will have to plug in 1 by r. Otherwise, you can think it as otherwise it will not be dimensionally consistent, right? So you see this has a dimension of 1 by L, but if you had just plugged in 1 by theta, the theta is just an angle. It is a dimensionless angle, right? So you will have to properly plug in some 1 by r so that you match the dimensions, and then you can add or subtract anything. Okay. So the quick example of this kind of potential which depends on this plane polar coordinates is, as you know, the dipole, right? For the dipole, what you have is you have p cos theta by r square. Okay. So here for brevity, I am writing the 1 by 4 pi epsilon 0 as k. Okay. Yeah. So what we will do here is, so yeah, at any point if you feel that you don't understand any of this, please let me know. Okay. I'll repeat as much as you want. Okay. Okay. So okay. So for right. So let's calculate the electric field for this potential. Okay. So first of all, we will take a derivative with respect to r. Okay. So there is, you see, so what I mean here is del r. That means that the cos theta, you can consider this cos theta is a constant here. So like when you do the derivatives of ddx, c times x, right? So this c, if this c is a constant, this comes out of the derivative, and you take the derivative of this x. So similarly, so when del r, this acts on this cos theta by r square, then you can directly bring this cos theta out of this derivative. This del r doesn't act on this r, or on this cos theta. You will have to just take the derivative of 1 by r square. So yeah, so only the derivative 1 by r square gives you r cube by 2, so 2 by r cube, right. Now for the second term we have 1 by r del theta and theta hat. So here what we get is we will have to just take the derivative of cos theta, and r square here we will think of this as a constant. Okay, so r square comes out of this whole thing, and there was a r sitting here, so we get r cube. See, everything is dimensionally consistent, and then cos theta's derivative gives us a minus sin theta, so that cancels out this minus, right. So this is the expression that you will probably find in some of the books. When you write the electric field of dipole, you get this kind of expression. So if you want to write this in Cartesian coordinates, then that will be a mess, right, because that will not have this kind of symmetries. So it is always better to write this kind of I mean you write those things in the symmetric coordinates, so then it will be nicer to look at, right. So yeah, so just remember this part. So when you are given a potential which is a function of r and theta, then you have to take a derivative in such a way. Okay, yeah. So just remember this part. Okay. Okay, so let's move on to the next one. So a particle of charge q is fixed at point P, and a second particle of mass m and same charge q is initially held a distance r1 from P. The second particle is then released. Determine its speed when its distance it is a distance r2 from P. Okay, so right now we are going inside this energy problems, right? So work energy kind of problems. So in all of these problems, what we always have to do is we have to balance some energies, right? Because energy is conserved. Energy is a conserved quantity. So we'll think about what was our initial configuration of charges. So we'll calculate the initial energy from that initial configuration, and we will see what is our final configuration of charges, and we will calculate energy for that configuration also. So initially you see that this q, yeah, I forgot which is this q1, but yeah. So initially there was only this potential energy, right? Initially the charge was fixed, right? So the q is fixed at point P. So there is no kinetic energy. Okay. Now the second particle is released. Okay, so that release, that means finally it will have obtained some kinetic energy, right? Now you just solve this equation. You solve for v, and you know what is the velocity at this point r2, right? So you just plug in those numbers, the mass, q, r1, r2, epsilon 0, all these things, and you obtain the number, right? So this is the main basic recipe of how to do these things for the work energy problems. Okay, very easy, very easy. Yeah, try to wrap your mind around this. You will have to just calculate the energies at 2 points. Okay. Okay, so let's move on to the next one. Yeah, a little more interesting problem. Okay, so a charge minus 9 nanocoulomb is uniformly distributed around a thin plastic ring lying in an YZ plane. So yeah, so I have tried to yeah, draw it, but my drawing is not that good. But yeah, think of this circle that this is lying in this YZ, in this okay, so this is in YZ, yeah, so this is in YZ plane, right? So this is the plane, yeah. So when there is, okay, and a particle is located at x-axis. So this is the particle, this is the q1, yeah, this is now. So a particle is located at this x, okay, x-axis at x is equal to 3 meters for a ring of radius 1.5 meter. Okay, yeah. Okay, how much work must an external force do on the particle to move it to the origin? Okay, so again, so we have two configurations. So this is our initial, and this is our final configuration, right? So we can calculate the net energy of this configuration. We can also calculate net energy of this configuration. Okay, so for like this example, when there is this q is situated here, then we can calculate the potential energy, right? So the potential energy for this thing is given by q1 q2 by r squared plus x squared square root and times 1 by 4 pi epsilon 0, obviously. So this is our initial configuration, right, when the charge was here. and finally what we have is our charge actually moves to the origin, and we will have to find the work done on the charge, okay, to move that charge from here to here. So for this thing that is very easy. So for this configuration we have to just do q1 q2 by r, okay. So we know the initial and final thing. So the work done is determined what is the final configuration minus what is the initial configuration's energy, potential energy, okay. So yeah, this is the expression, and so you can go ahead and plug in all of this q1 q2 r etc. okay. Okay, okay, some more problems, right? So yeah, some more problems on this energy conservation. Okay, so what is the escape speed for an electron initially at rest on the surface of a sphere with radius 1 centimeter and a uniformly distributed charge of 1.6 into 10 to the power minus 15 coulomb? That is what initial speed must the electron have in order to reach an infinite distance from the sphere and have zero kinetic energy from when it gets there, okay. So initially there is a sphere. So the sphere has some charge, right, and there is this q, okay. Now so what is the initial speed that it needs to go to escape from this sphere, right? So how do we get that? So this is the initial energy, right? So that the charge was still on the surface, it didn't have any kinetic energy, right? But when it moves to infinity, then at infinity we assume that there is a potential energy is 0. So at infinity this electron will have only kinetic energy, right? So I mean these guys have to balance. So this is your initial energy and this is your final energy. Finally the particle doesn't have any potential energy. So from here you see you will have to just solve for this v, right? You have to just calculate the v and you will find what is the escape velocity of this charge. Okay, okay, so let's move on to the next one. Okay, okay, so yeah, this is the figure, shows an electron moving along an electric dipole axis toward the negative side of the dipole. The dipole is fixed in place. The electron was initially very far from the dipole. So you see the very far, this means that initially we didn't have any kinetic energy. The whole energy was okay. So initially we didn't have any potential energy. The whole energy was kinetic. Okay, so very far from the dipole with kinetic energy 100 electron volt. So you can assume that this is the net energy, right? Because when the particle was at infinity, it didn't feel any force from this dipole. Okay, because for the dipole the potential is, it goes as 1 by r square, and when the r is very very large, then you can always neglect this potential effect on this charge. Okay, okay. So this figure gives a kinetic energy k of the electron versus its distance r from the dipole center. Okay, so this axis is the r, and there is a scale. The scale is given by rs. Okay, what is the magnitude of the dipole moment? Okay, so okay, so first of all we'll have to balance those two energies, right? So energies at the infinity, right, and energy at some point on this curve. Okay, so you see, first of all, when you look at this diagram, you see so they have only drawn up to rs, but this actually goes asymptotically, right? So it goes like that. Okay, so here this energy rs is given by 100, so the kinetic energy is given by 100 electron volt. Okay, but as you go here, so here means that is around 1 by 5 rs. So when you go here, you see the kinetic energy has almost vanished. So there is no kinetic energy. The kinetic energy is 0. So what does that mean? That means that if 100 electron volts was my initial total energy, that means this final energy will also have to be 100 electron volt. But we see that there is no kinetic energy, right? That means all of this 100 electron volt that goes into the potential energy. Okay, so what we will do here is we will just write the potential energy due to this system. Okay, and we will equate with 100. Okay, because we only want the potential energy. So okay, U is equal to QV, right? The potential energy is Q times the potential, and we have this charge, right? And also there is this this potential due to the dipole. Okay, so so you just plug in those values. The theta is 180 degree because it is directly coming from this side, right? And just you will balance it 100, right? And so there is 1 by E to convert this whole energy to electron volts. Okay, so by dividing E, we have converted this whole energy into electron volts. Okay, so now what you will do is they have asked to calculate the dipole moment. Okay, so the dipole moment, you just solve for this P and you will have the dipole moment. Okay, okay. So yeah, I think we can fit in. Yeah, so that is a large problem. Okay, so let's give it a try. Okay, let's try to do this. Okay, so suppose electrons can be placed in either of the two configurations. In configuration 1, they are all placed on the circumference of a narrow ring of radius r and are uniformly distributed, so that the distance between adjacent electron is the same everywhere. Okay, so that means you have a ring and you uniformly distribute the charges. Okay, so in configuration 2, there is n minus 1 electron are uniformly distributed on the ring, and 1 electron is placed on the center of the ring. Okay, so they are talking about the other configuration now. Okay, so what is the smallest value of n for which second configuration is less energetic than the first? Okay, so we'll have to compare these energies, right? Now here the tricky thing is, because we want to compute the energies, right? So first of all, we will have to think about how many combinations are there, because you see all of the potential energies come like in a pairs, q1 q2 by some distance plus q2 q3 by some distance, right? So we'll have to figure out what is the total number of combinations that we can have out of these n particles. So what we will do is we will calculate this nc2. So this nc2 will tell us if we have n number of particles, and out of those n numbers, if we take two particles, if we just combine two particles, what are the net possible terms we will have. So there are n minus 2, n times n minus 2 by 2. Okay, this number of terms that we will have in the summation. So electrostatic energy is given by Q times B, and the summation goes from I is equal to 1 to n minus 2 by 2. So we'll have to figure out all of these potentials for all of these Ri's, right? Then we can just sum it up and we can get that electrostatic energy, right? Seems easy, but it is not that much easy. So these Ri's are actually a little tricky to calculate, right? So these Ri's are just these numbers, right? So how do you calculate these numbers? How do you calculate this distance? So to calculate this distance, we will have to use the laws of sines, sines. Okay. So the laws of sines tells you that if you have a distance x here, and the angle is theta by 2 of this larger triangle, then their ratio will give you 2r, twice the radius of this thing. Okay, so this is, you can just look up the laws of sines. I think you know already this. So you just solve this x, right? Okay, so when you solve this x, you know if there is a theta angle between these two particles from this center, then the distance is 2r sine theta by 2. Okay, but there is not only two particles, there are some n number of particles, right? So we'll have to calculate separation for each pair. So here I am writing the separation with an index j. So when you will change this j, you will obtain all of these distances. Okay, so okay, you plug in all of these rj's, right? So here you see I have plugged in the sine theta. Okay, and so you can calculate this energy. Okay, so you can calculate. Okay, so yeah, so this is for the first configuration where all of the charges are on that circle. Okay, and this is for the other configuration where all of the charges are not on the circle. So the difference will be that the thetas from these two problems will be somewhat different. So this theta for the previous problem was n by 2 pi, and for this problem that will be n minus 1 by 2 pi. Okay. Okay, so the number of combinations will remain same because the total particles are all still n, right? But you see that you cannot directly sum over this 1 by sines. I mean, there is no way to do it by hand. You will have to use some sort of calculator. Okay, So you find some sort of calculator, you try to make a table out of this thing. Okay, you tally these two energies, and that is the only way to find the n, which n will minimize the energy, something like that. Okay, so yeah,